Okay, hey everyone, welcome back. This is part 3 of control circuits. If you have not listened to watch part 1 or 2 yet, please go and do that before you continue. I'll wait right here for you. Welcome back. So we've got 12 slides to go, so let's finish this one off and then you can do the test. Remind me before the end of the video to give you the remainder of the code that you'll need. Okay, so we left off at the end of the last video. We were just briefly talking about two-way switches, two-way lighting circuits. So this is where a single light or a single lighting circuit, so multiple lights looped together, can be controlled from two different places. It's often used in hallways and stairs. So when you walk in, you can switch the lights on. When you walk out the other end, you can switch the lights off. But any room where we have more than one exit and entrance is a useful place to have two-way lighting. So you can enter one way, turn the lights on, exit somewhere else, turn the lights off. So we've got a nice little picture here of a two-way lighting circuit, and what we have in all two-way switches, or two-way switching circuits, is a switch and a second switch, two switches, a light, and a feed coming from our switchboard, and what we call straps. So these are the conductors that will connect the two switches. So there's a couple of ways of doing it. We have like what we call a two-way and a three-way, or a two-strap and three-strap system rather. A three-strap system allows us to utilize, or allows us to have the feed coming in from the switchboard and the control going out to the light coming from the same switch, which is really useful if we are doing a retrofit. So we're putting two-way lighting into an existing installation where the switching is currently one way. So that means that I only need to get a cable from my old switch to the new switch. I don't have to get any cables back to the switchboard. I don't have to move the switch. I don't have to move the control wire from one switch to the new switch, from the old switch to the new switch. So I just have to run one new cable from my old switch to wherever I want the new one. And I'm going to use 3 cores to do it. So you can see this here, this one here, live feed coming in from switchboard. That may be existing if we're doing a retrofit, and then we have the control wire going out to our light. Again, that would be most likely existing. The neutral here, obviously it's showing going back to neutral. In reality it's in this cable, so it'll come back here, and inside the switch we'll have that going to a loop terminal and then back out to neutral on the same cable as this one. The new switch that we put in, we will put a 3-core cable in there, and we're going to connect terminal 1 to terminal 1, terminal 2, terminal 2, common goes to common. If you wish, you may sit here and look at this slide, perhaps pause the video and just have a think about where those switch positions would be, on, off, and we can follow the current flow. In this switch position here, for example, we're having the live feed coming into number 2. It goes across to number 2 on the second switch, to common, back down here, to common on the other switch, across to number 1, and up to the light. So with the switches in these two positions, the light's going to be on. So if you wish to, you can pause this video and just think about the different permutations of the switches, and you'll find that as we switch the switches in any position, whatever we do, if we change one, it's going to change the state of the lights. That's what we need for two-way lighting. If the light's on, I want to switch any switch and it'll go off. If the light's off, I want to switch any switch and it'll go on. The other method, the two-strap method, is on this first slide here. So that's our two-strap method. This is what we would usually do in a new building. So we've got a feed wire coming in from the switchboard, two straps going across to the second switch, and then a control wire out to the light. You can see why this would be less useful in an existing installation, because in an existing installation, switch number 1 will have the feed coming in from the switchboard and also control going out to my light. Just be aware when you're using a three-strap method like this, that if you use a normal black, red, green TPS cable, that is illegal. It's illegal because all three of these cables that are running from one switch to the other are conductors, or active conductors, and we cannot use green for an active conductor, not even if we sleeve it at the ends. It must not be green. So you're going to need to get strap cable, which will be blue, white and red, usually blue, white and red cables in it for you to so you can have three active conductors. Multiple switching control. If one light is to be controlled from 3 or more positions, a combination of two-way and double pole changeover switches can be used. This is also known as an intermediate switch. This circuit is shown below. The intermediate switch has 4 terminals which are connected by the straps between the two-way switches, so that when operated, the straps simply swap over. Any number of intermediate switches can be introduced between the two-way switches, giving each completely independent control. So we have our, this is our normal two-way switch here. And we have our changeover intermediate switch here. So this is our switching part here. So that switch can switch upwards, so it connects to this. This switch can switch upwards, so it connects to this. And then this will be our second two-way switch here. So it can change from one side to the other. This gate gives us the same ability as the two-way switching. Whatever state the light is in, if it's on, I switch any switch, it goes off. If it's off, I switch any switch, it goes on. When we're back in class and we're doing practicals, we will have a look at an intermediate switch at least once. This is if I want to use 3 switches or more. And then if I want 3 switches, I have a two-way switch, an intermediate, and then a two-way. If I want more than that, then I have a two-way switch, and then however many intermediates I want, and then a two-way switch at the end. So it's always going to have a two-way switch where the phase comes in, and a two-way switch where it goes out to the light, and then intermediate switches in the middle, as many as I want. Automatic control. So here we have a start-stops button, start-stop switch. Powering a coil, which will power our lights. If we look here, we've got phase coming in, running through my start circuit. I've got there the start button and the hold-in contact, and the main contacts powering my load. At the moment, they're all open. If I push the start button, power flows through here, energizes the coil, closes the contact. Contact closes, light turns on. Just like we talked about before for motors or whatever, but we could use that for running lights as well. It's not very common, but you could use it. And here we go. That's the operating sequence there, just as I've just described it, and exactly the same as we've previously described it for the motor starter, direct online motor starter, or what have you. Okay, 3-heat switching. 3-heat switching is where we have 2 heating elements, and we use different combinations of those elements, whether they're 1 or 2 elements or in series or parallel. to give us different heats. A common application of this you would find on an electric blanket. Electric blanket is the most common place that you'll find 3 heat switching, if you think of that in your mind. If you have no idea what I'm talking about because you've never had or used an electric blanket, you haven't lived, my friend. But for those of you who have, think about that switch that you'll have on the electric blanket, and it has 3 settings. This is a 3 heat switch. So the heats are available at full, which is high, medium is half, and low, which is quarter. When the switch is in the high position, the two elements are connected in parallel. So they both get the full voltage, and they both produce full heat. When you go to the medium position, only one element is energized, so you get full heat but only on one element. When you have the switch in the low position, the elements are going to be connected in series. So the volt drop in that series circuit means that each element only receives half the voltage and therefore only produces a quarter of the heat. So that's how a 3 heat switch works. And here is the diagram here. If you have a look, switch on low, what have we got? Power coming in from into number 1. Number 1 is our power in, and we're switching what are we switching? Wait a minute, give me a second here. Sorry. So we have power coming in on L1. It's going to, in this position, L1 is switched to 2. So it runs through there, through this element, through here, back to here. Terminal 1 isn't touching anything, but we do have a connection here to the other element. So essentially we're running from 2 through one element, following all the way around through the other element, back to terminal 3, and that's going to neutral. So we have both of the elements in series with each other. In the medium, we have power on L1 switched to number 1. It will go through here, here, so we have this element on because that's connected back to neutral. This element here, we've got power feeding to that element, but if we look here, it goes, the neutral comes back to number 2, and there is no connection on number 2, so then that top element is not connected to anything. And on the third one here, we have L1 is connected to 1, neutral connected to 3 and 2, so we have 2 paths here out of 1 to that element, and 1 through here to this element. Neutral is connected to 2 and 3, which connects this end of this element is connected to 2, this end of this element is connected to 3, so both of them have a path back to neutral, which means that they are in parallel with each other. Simmerstat control. So Simmerstat is another type of, similar to a thermostat, it's a heating control switch. Energy input to an appliance can be varied by controlling the ratio of on to off switching intervals over a period of time. Simmerstat is a switch that has a quick cycling mechanism. This opens and closes its contacts continuously in time on and time off proportions. The proportions depend on the setting of the control knob mechanism. The regular on-off switching cycle works by a bimetal switch bending under the influence of heat from a timing element attached to it. The graduated knob operates a cam that moves the bimetal assembly to alter the ratio of on to off time. So basically what we're saying here is that the Simmerstat is going to continuously turn on and off. It will just turn on and off. And then that, if we're, for example, controlling an element on the top of an oven, then when it turns on and off, it's never going to be fully on and it's never going to be fully off. Just imagine the switch going on, off, on, off, on, off. So it's going to give that oven element some sort of, kind of a medium heat. on, off, on, off, on, off. And when we turn that Simmerstat, it's going to move the bimetal a little bit to alter the ratio of on and off time to either give us more on time, which will be hotter, or more on time, off time, which will be cooler. Obviously, if we go to the point where it's continuously on, then it's as hot as it'll go. If it's continuously off, it'll be not working at all. But in the middle, some on, some off, on, off, on, off. I don't know if it operates that fast. It might switch every 30 seconds, every minute, who knows. But by altering that on and off time, it gives us a medium heat, and we can alter that medium heat to be a bit hotter or a bit cooler. So this is really useful for temperature control in, as I say, something like an oven where you want, you don't quite want to use a thermostat, because the thermostat is going to give full power until the element gets hot enough, and then no power until it cools down, where this way it's going to give you some sort of moderate heat, so you can have it keep your whatever you're cooking simmering, for example, keeping it at a warm temperature but lower than full bore. Yeah, I hope that makes sense. And here's a picture of a Simmerstat and the diagram there. So there's our timing heater, bimetallic strip, so on and so forth, and providing power to the range element there. Alright, temperature control. Temperature control is a process in which change of temperature of a space and objects collectively there within is measured or otherwise detected, and the passage of heat energy into or out of the space is adjusted to achieve the desired average temperature. The thermostat is an automatic switch that responds to temperature. It is used to control an electric heating appliance so that a definite temperature is maintained in whatever is being heated. It does this by switching the appliance off when a higher temperature is reached and on again at a lower temperature. There are many kinds of thermostat available, and all are designed for specific purposes. Let's look at type commonly used, called the electro-mechanical thermostat. So let's just have a think about what a thermostat is doing. It should be fairly obvious. I'm sure all of you have come across a thermostat before and have a reasonably good idea of what it's doing. But let's think about that concept. So when the thermostat heats up to a set temperature, it will switch off. When it cools down to that set temperature, it will switch back on. The thermostat is set up to measure the temperature off whatever it is that's being heated. If it's a hot water cylinder, then we have to have our thermostat stuck next to, on top of the hot water cylinder. If it was a heater, it's inside the heater. If it was a air conditioning unit or heat pump, then it's inside the heat pump. It's a fairly coarse measure of temperature control, because obviously it is going to just go full bore while it's on, and then nothing while it's off. Although there's some exceptions to that, which I'll talk about shortly as we go through these slides. Yeah, look, the important thing to understand is that we need to, in order to get accurate temperature control, we need to have a really good connection, I guess, between the thermostat and whatever is being heated. Otherwise, it's not going to work very well. And we need to understand that the thermostat is coarse control, because it just switches on and off. And in fact, it's not even going to switch on and off at a specific temperature. If I set the thermostat to say 24 degrees, and it's switched on and off at 24 degrees, then as soon as I hit 24 degrees, it switches off. And then as soon as it drops by 0.1 degree, it switches back on. So it'll just be constantly switching on and off, which would be hopeless. It would be hopeless. So usually you'll have the word is hysteresis, which is the variation between the on and off time. So if I set it to 24, it's probably actually going to switch off at like 26 degrees and switch back on at 22 degrees. It'll be plus or minus 2 degrees, something like that. So then I'm not even going to get 24. All I can say is, well, it's probably somewhere between 22 and 26. Okay, so the thermostat comprises a mechanical temperature sensor and an electric switch. The sensors vary in design and construction, but all work on the principle that solids, liquids and gases expand or contract with temperature. A temperature switch or thermostat is used to sense temperature changes, excuse me, and is actuated by some specific environmental temperature change. Here we go. The basic circuit operates as follows. The isolator is closed, contactor is energized via the thermostat as the water is below the set temperature. So this is in the example of a hot water cylinder. The contactor contacts close, energizing the heater element. The water heats up to the set temperature. The thermostat senses this, so the thermostat has some sort of connection to the water, and therefore when it opens, it de-energizes the contactor and that disconnects the heating circuit. Thermostat turns on again if the hot water is used or it drops below a minimum temperature. Pretty straightforward. So you can see there that the process is going to be fully automated. So the contactor there, thermostat, water heating element, it'll just run by itself forever unless I switch the isolator off. You can follow those wires yourself to figure out where everything is going. It's not too complicated. And that is the end of that slideshow. So I need to give you the code. So we already had in the last video the first 2 digits of the code. Second 2 digits will be 28. So you should already have the first 2. That's in the last video. Second 2 digits of the code are 28. So you should now have 4 digits. That is the code. You can go and do the test. As ever, you all have my contact details. If you need a hand with anything, please feel free to give me a bell. Until next time.